Hello students, and welcome back to another geometry video. You know what to do. Pause the video and try these problems in your notes, then unpause it to do it with me. Okay. Alrighty, the vertices of JKL are as follows. We want to graph JKL and its image after a reflection in the x-axis and after a reflection in the y-axis. So, first thing, let's graph JKL in the coordinate plane. So K is at 4, 4, and L is at 3, 1. Perfect. And let's do it over here too. We can save on some time. K is at 4, 4, and L is at 3, 1. Okay. Perfect. So first, we have J, K, and L. Now, we want to transform J, K, and L by reflecting over the x-axis. So, what we're going to do is we're going to take J, K, and L, and we're going to make a J prime, K prime, and L prime. So, when we reflect in the x-axis, we make the y values negative. So I'm going to write the exact same points, except all of the y values will be negative. So now let's graph J prime, K prime, and L prime. 1, -3 is J prime. 4, -4 is K prime, and 3, -1 is L prime. Do these triangles, the red triangle and the blue triangle, look exactly the same? Yes. Yes, they do. And they have been reflected over the x-axis. So perfect. Awesome. Let's go ahead and move on to the y-axis. We have J, 1, 3, K, 4, 4, and L, 3, 1. And we want to transform these into J prime, K prime, and L prime. The way that we're going to do this, if I'm reflecting over the y-axis, it means that I'm making my x values negative. -1, 3, -4, 4, -3, 1. And let's graph these points in the plane. -1, 3 is J prime, -4, 4 is K prime, and -3, 1 is L prime. Retry that line. Goodness. Connect the dots. And do those triangles, the blue and the red triangles, look exactly the same? Yes. Yes, they do. So, we are good. We are done. Time to start what we have for today. Today, we're moving into section 4.3, the third section of chapter 4, and it is all about rotations. So our learning target is that you know what a rotation is and what rotational symmetry is. And the success criteria is that you can perform rotations in the coordinate planes and you can identify rotational symmetry. So very similar to our 4.2 learning target and success criteria, but then we had reflections and line symmetry. Now we have rotations and rotational symmetry. So you could even pause the video right now and think, how will they be the same? How will they be different? What do you think? And then unpause it, and we'll keep going. A rotation is a transformation. Remember, chapter 4 is all about transformations. A transformation in which a figure is turned about a fixed point. So here we have this shape, kind of like a flag, in the blue, and we have rotated it. We've turned it 40 degrees to the left, or 40 degrees counterclockwise. So we call the number of degrees that you turn the object, we call that the angle of rotation, and the point about which you rotate. So here I'm rotating from my elbow. We call that the center of rotation. For our class, the center of rotation will always be the origin, the middle of our graph. But you can have a different center of origin. Okay, so let's move on to a little bit more about rotations. So, a rotation is a transformation in which a figure is turned about a fixed point, called the center of rotation. That fixed point that it turns around is the center of rotation. The doorknob, right, when you turn the doorknob to open a door, the center of rotation is where the doorknob attaches to the door. Rays drawn from the center of rotation to a point and its image form the angle of rotation. So if you take a ray from the center of rotation to Q and a ray from the center of rotation to Q prime, this is what makes the angle of rotation. Whatever the measure of this angle is, in this case it's 40 degrees, that is the angle of rotation. Okay, and again, this is for if you want more of a challenge, read this and understand this. Pause the video and look at the screen. If you want more of a challenge. If you don't want more of a challenge, that's okay. Keep on chugging with me. So, more important information. Rules. You remember our rules for translations? They looked something like this. The rules for our reflections looked something like this. Now, so we'll write that. Translation, reflection. Reflection in what? The x-axis or the y-axis? X-axis, because the y values are negative. Okay, now these are what our rules look like for rotations. So for rotations, if you want to rotate 90 degrees, take your point, switch the x and the y, and make the y value negative, or make the first value negative. For 180 degrees, take the point and make them both negative. Make A and B negative. For 270 degrees, take the point, switch A and B, and make the second one negative. Now, it's easier said than done, right? Trying to remember all of this can be kind of confusing, but the more you practice, the better you will get. Another thing that we need to say about rotations is these rules are for rotating counterclockwise. In math class, whenever we talk about angles, rotations, we're talking counterclockwise. And that's because the up, or the positive direction on the y-axis, is up. So whenever I talk about angles, I want to talk about them starting at the x-axis and going up. So that's why we go counterclockwise instead of, if we started counterclockwise, we'd be going down, and then we'd have like a negative angle. And we don't want to talk about negative angles yet. You'll do that in trigonometry. But for now, we want to talk about positive angles. So we'll go counterclockwise. Now, for those of you that want a little bit more of a challenge, you can think about this. A 90-degree rotation counterclockwise is the same thing as a 270-degree rotation clockwise. A 180-degree rotation doesn't matter whether it's clockwise or counterclockwise, right? It's the same. And a 270-degree rotation, counterclockwise, is the same as a 90-degree rotation, clockwise. And CC stands for counterclockwise. So that's something that you folks that want a challenge can think about. Okay, but let me erase that so we don't confuse anybody. All right, counterclockwise. Unless you are told otherwise, we are going counterclockwise, and these are the rules that you'll use. So, without further ado, let's start on our first example, rotating a figure in the coordinate plane. Graph quadrilateral RSTU with these vertices and its image after a 270-degree rotation about the origin. Now, it didn't say clockwise or counterclockwise. We always assume counterclockwise. Counterclockwise. So let's start. We have R, 3, 1, S, 5, 1, T, 5, negative 3, and U, 2, negative 1. Let's graph these on the coordinate plane. 3, 1 is R, 5, 1 is S, 5, negative 3 is T, and 2, negative 1 is U. Connect the dots. Okay, now we want to map this, or to transform it 270 degrees counterclockwise. So we want to find our R prime, S prime, T prime, and U prime. Now, what was the rule for 270 degrees? I took A, B, and then how did I change them? Now, we can go back up here and look. AB means I take B, negative A. Now, for your tests, I might give you this. I might make you memorize it. I might make you remember it. It depends on your teacher, right? So, try to remember these if you can. Maybe you'll get them on your tests. Maybe you won't. I don't know. Okay, so what we're going to do is we will take A and B, and we're going to switch them. AB becomes BA. So 3, 1 becomes 1, 3. 5, 1 becomes 1, 5. And so on. But also, the A, or the second one, becomes negative. So instead of 1, 3, I'm going to have 1, negative 3. Instead of 1, 5, I'm going to have negative 5. So switch A and B and make the second one negative. So for T prime, we'll have negative 3, 5, and make the second one negative. Make the 5 negative. For U prime, we'll have negative 1, 2, and make the 2 negative, because it's the second number. Okay, and now let's graph our points. 1, negative 3 is R prime. S is 1, negative 5. T is negative 3, negative 5. T prime, excuse me. And U prime is negative 1, negative 2. Ooh, let's try that again. Straight lines, straight line. Okay, and there we go. Now, think in your mind, if I am rotating 270 degrees, that means I'm going 90, 180, 270. So I'm going 1, 2, 3. I'm doing 90 degrees 3 times. So if I took U and I rotated it 90 degrees, I would be here. Here would be U prime. If I did 180 degrees, here would be U prime. And if I went 270 degrees, here would be U prime. See how each of these makes a right angle right here? So that's a way that you can check in your mind. You can say, wait, is this actually a 270 degree rotation? Well, you can try 90, 180, and then 270. Is it? Does it look like a 270 degree rotation? Yes. Yes, it does. One more thing I want to say about this example. We switched the coordinates and made the second one negative. What if I gave you a point? What if I gave you -3, 4? And we'll just call it Q. When you go to make Q prime, you're going to switch the coordinates. So we'll have 4, -3. And then you make the second one negative. But it already is negative. Well, remember, if you make a negative, you take a negative number and you make it negative, negative and a negative, make a positive. So, if the number's already negative, change it to a positive. Okay. And we'll write that. If already negative, turn positive. Okay. Awesome. Awesome, awesome. Let's check and make sure that we were right. Beautiful. 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 Okay. We were indeed correct. Now, let's move on. Example 3 is performing a composition. This is the third time that we've heard about compositions. The first, we saw a composition of translations. So one translation and then another. In 4.2, we saw a glide reflection, which was a composition of a translation and then a reflection. And now we're seeing a composition of a reflection and then a rotation. You can have compositions of these 3 transformations, translations, reflections, and rotations. You can see compositions of these in many different ways. You can reflect and then rotate. You can translate and then rotate. You can reflect and then rotate. You can do whatever you want to do. You can do it in whatever order that they tell you to do it in. So, in this example, they're asking us to reflect and then rotate. So, let's take segment RS with the following endpoints. So we have R, -1, 3, and S, 2, -6. Let's graph that. 1, -3, and 2, -6. So here's RS. Now, it wants us to reflect in the y-axis. What is the rule for this? I take x and y and I make, which one do I make negative? The x values become negative because I'm reflecting in the y-axis. So, my coordinates for r prime and s prime after I do the reflection are -1, -3, and -2, -6. Let's graph these. -1, -3 is r prime, and -2, -6 is s prime. Does that look like a perfect reflection? Yes? Yes, it does. Awesome. We're done with our reflection. Now, we want to rotate 90 degrees about the origin. Now, what was the rule for 90 degrees? Well, remember, I'm going to flip B and then A, and I'll make the first one negative. And remember, we had the slide up here that showed us 90 degrees. This is the rule for 90 degrees. Flip A and B and make the first one negative. The way that I remember it is it goes 90, then 180, then 270. Because 90 comes first, I make the first one negative. Because 270 comes last, I make the last one negative. And that's how I like to think about it. If that helps you, yay! Okay, back to the example that we're on here. So, to make R double prime and S double prime, I'm going to switch the coordinates. So 1, -3 becomes -3, -1. And then I'm going to make the first one negative. It's already negative, so I'm going to make it positive. For S, I'm going to switch them. -2, -6 becomes -6, -2. And I'm going to make the first one negative. It's already negative, so I'll make it positive. Okay, and let's graph these points. R prime is 3, -1. R double prime, excuse me. And S double prime is 6, -2. Ooh. Let's try to make that line as straight as possible. As straight as possible. Good enough. Okay, so you can see, first I reflected and then I rotated R prime 90 degrees. So I went from the origin to R prime, from the origin to R double prime is a 90-degree angle. Counterclockwise. Awesome! And we finished our rotation. Let's check and make sure we were correct. Beautiful. That's what our graph looks like. And we did our points just like they did, and our graph looks just like theirs does. So yay! We were correct. Alright, the last thing that we're going to talk about in this lesson is rotational symmetry. Remember that our learning target and our success criteria asked you to know, to learn what a rotation was and what rotational symmetry is. And our success criteria said that you needed to identify rotational symmetry. So that's what we're going to focus on in the next half of the lesson. Rotational symmetry. A figure has rotational symmetry when the figure can be mapped onto itself. We talked about this with line symmetry. It means it looks exactly like itself when you're done mapping, or when you're done with the transformation, it looks exactly like itself, by a rotation of 180 degrees or less about the center of the figure. Now, that is a lot of words. Let's break it down. The center of the figure. For example, this parallelogram, the center of it is right here at this point. Now, if we can spin this shape or rotate the shape 180 degrees or less and have it look exactly the same, it has rotational symmetry. So, for this parallelogram, it does have rotational symmetry because a 180-degree rotation about the center maps the parallelogram onto itself. If I take this point and go 180 degrees, and remember, 180 degrees is half of a circle, so I'll go half a circle around. If I flip this shape around 180 degrees, it looks exactly the same. If I only flipped it 90 degrees, Well, it wouldn't look the same. Then it would look like this, right? And that doesn't look exactly the same. But when I flip it 180 degrees, it does look exactly the same. So, it has rotational symmetry with 180 degrees. Now, we're going to talk more about rotational symmetry on this slide. A figure in the plane, or a shape in a plane, has rotational symmetry when the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. The center of the figure is called the center of symmetry. And note that this rotation can be either clockwise or counterclockwise. Typically, we will look counterclockwise, but when it comes to rotational symmetry, it doesn't really matter, because if it has rotational symmetry counterclockwise, it will have rotational symmetry clockwise. Okay, so for example, here's another example. The figure below, this pinwheel, and we've seen those rotate, right? When you blow on them and they spin around. The figure below has rotational symmetry because a rotation of either 90 degrees or 180 degrees maps the figure onto itself. A rotation of 45 degrees does not. So I could rotate this pinwheel 45 degrees, but it won't look exactly the same. If I rotate it 45 degrees, notice that here the pinwheel has sort of a plus shape, and when I map it 45 degrees, it has more of an X type shape. So 45 degrees doesn't work, does not have rotational symmetry. But 90 degrees, these pictures look exactly the same, and 180 degrees looks exactly the same. So let's try our hand at another example. Identifying rotational symmetry, part of your success criteria. Does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. So, first, we'll find the center of each shape. Okay, now, if I spin, we'll just pick a point. If I spin this point 90 degrees, does that work? Well, no, this is the one we just talked about, right? Then it'll have the long way up, and we only want the long way side to side. So, 90 degrees doesn't work because I do not get the same shape. But 180 degrees, if I spin it, will give me the exact same shape. So yes, this parallelogram does have rotational symmetry. And describe the rotations. 180 degree rotation maps it onto itself. We don't need to say clockwise or counterclockwise. We don't need to, because it'll work counterclockwise or clockwise. It'll work the same. New color. The octagon. Let's pick a point here. If I rotate it over here and I shift the whole shape around like this, will I get the same thing? Yeah. Yeah, it'll just put this side here, this side will go here, this side will go here. Yeah. So, this rotation works. Is that a 90 degree rotation? No, it's not. This would be a 90 degree rotation, which also works. What is half of 90? 45. The way I remember that is half of a soccer game is 45 minutes, and soccer games are 90 minutes. Okay, so yes, 45 degrees. It would also work with 90 degrees It will also work with 45 plus 90 degrees, which is 130, yes, 135 degrees. It'll work with 180 degrees. It'll work with 180 plus 45, which is 225 degrees. It'll work with 180 plus 90. It'll work with 270. All the multiples of 45. This is 45 times 1, 45 times 2, 45 times 3, 45 times 4, 44 times 5, 45 times 6. Oops. And we can even do 45 times 7, 315 degrees. But if I do 45 times 8, I'll get 360 degrees, and anything has rotational symmetry with 360 degrees. So we don't include 360 degrees. Because everything, if you turn it around 360 degrees, well, yeah, it looks exactly the same. Okay, perfect. So that is all of them. Let's pick a new color and we'll move on to the trapezoid. All right, let's pick this point. If I rotate it 90 degrees, that puts the shape like this. So no, that doesn't work. If I rotate it 180 degrees, I get this. Nope, that doesn't work. If I rotate it 270 degrees, nope. The only way that this trapezoid can look like itself is if I go all the way 360 degrees. But anything has rotational symmetry with 360 degrees. So that doesn't count. No. The trapezoid does not have rotational symmetry because I can't spin it and get the same thing unless I spin it all the way around. Okay, let's check and see if we were correct. So, parallelogram, yes, 180. Octagon, 45, 90, 130, 180. They didn't include anything after 180, and that's because, remember, if you do 45 degrees clockwise or 45 degrees counterclockwise, that's the same thing as 350 degrees, or excuse me, 315 degrees in the opposite direction. So you don't have to include these last three, but I like to. Okay. And the last one, trapezoid does not have rotational symmetry because no rotation of 180 degrees or less maps it onto itself. So no. Yay! We were right. That is everything I have for you today. If you have questions, please make sure to raise your hand, which virtually looks like sending an email, coming to office hours, asking for help. I wish that I could see your hands raised, I could see your confused faces, but I can't always with the virtual learning. So please make sure you're asking for help if you need it, because I might not know you need help until you ask for it. So please, please, please ask questions. If you'd like to practice any of the skills learned in this video, these are some problems that you can do to help you practice. Remember that these might be different than the problems your teacher assigns, so be sure to do the homework that your teacher assigns, but you can do these too if you'd like. As usual, let's end our lesson with a launch. Today's launch comes from Dolly Parton. She's a famous country singer, and she says, if you don't like the road you're walking, start paving another one. If you don't like the road that you're walking, start paving another one. Now, I know this isn't always possible, right? It's not always possible to pave another one. You can't control your family, the parents that you have, the house that you live in. When you're under 18, you can't always control who is the boss of you, right? Your parents, your teachers are the boss of you. So you can't control everything. But you can control the way that you react to things and the way that you think about things. So if there's something that you don't like about your life, you don't like being stressed out with homework, start paving another road. Find another way to organize your homework. Find another way to get it done in a shorter amount of time or on a better schedule so that you're not stressed out. If you don't like how your friends are treating you, go find new friends. Or put some boundaries around that says, hey, I can be friends with you if you don't treat me this way. I need to be treated this way in order for me to be friends with you. So if you don't like something about your life, you have the power to change it with your thoughts and with your actions. So if you don't like something about your life, change it. And if you don't know what changing it looks like, talk to somebody. Talk to a friend. See if how you can change the things that you don't like, because you have power over a lot more things than you think. That is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.